Hello, my name is Andrew Bechtel, and welcome to Civ 371, Civil Engineering Materials and Structures. This is a class where we tie together everything you've learned or are learning in your structural design courses to the material properties themselves, and we try to understand how the material properties affect the structural behavior. Now, since we're talking about materials, let's first talk about material science. Material science uses high levels of applied physics and chemistry. It studies the relationship between the structure of a material at the molecular level and its macroscopic properties. So at the molecular level, we look at how do we make new materials? What are the bonds between the different molecules in the material? What chemical reactions occur? What crystalline structures can we form? All kinds of things like that. In terms of civil engineering, the macroscopic properties we're usually talking about are what are the material properties and how can we use these material properties and how can we design for these materials. These are things like F prime C, Fy, E, the elastic modulus, T, the rupture strength. Now, I want to make it very clear that I am personally not a material scientist. I've never been much into chemistry or anything like that. But I have built a bunch of stuff and studied structures made from materials. And whenever you study any type of structure, you need to understand what the materials are. I've built large concrete beams. Here you see some inverted pier caps, and I was even so bold as to inscribe my initials into this one. So you can see the AB right there. This is a model of a pier cap turned upside down. Here you see that same thing, and I've reinforced it with carbon fiber. Here's a carbon fiber coupon that I've tested, so I've tested the properties of composites. Here's a concrete cylinder, obviously breaking the concrete. I've also built my own 1/4 scale steel bridge. Here you see steel girders. Forming up and reinforcement for the deck and pouring a deck, and then I loaded this tiny bridge to ultimate capacity. And in order to understand all the behavior and all these things I've always built, I have needed to do the material properties. So I cut coupons out of the steel and did tension tests on them. I even tested the wires in this reinforcement, tested concrete, rebar, composite, anything you can kind of build structurally, I've tried to test. So I have a lot of experience in understanding macroscopic material properties and how they influence structural behavior. Now, we're going to start with the most complicated civil engineering materials and then go to the least complicated civil engineering materials. And the most complicated civil engineering material in terms of material properties is reinforced concrete, because we need to understand how the concrete behaves and the reinforcement, which is generally steel. So when we look at reinforced concrete, we have a set of concrete properties, and we have a set of steel properties. When we look at concrete, we look at F prime C, which is the design compression strength, FCT, which is the tensile splitting strength, FR, the modulus of rupture, and E sub C, which is big E is always elastic modulus, sub C is the elastic modulus of concrete. When we include the steel, we have Fy, which is the yield stress of the steel, Fu, which is the ultimate tensile stress of the reinforcing steel, and E sub S, which is the elastic modulus of reinforcing steel. And since you've generally had steel design already, the elastic modulus of steel in the excellent imperial units is 29 million psi or 29,000 ksi. That's a number you can remember and always use. Simpler than reinforced concrete design is steel design. When you look at steel design, you really only think of three things. You look at the yield stress of the concrete, the ultimate tensile stress of that steel, and the elastic modulus of steel, which is still 29,000. Now, we need basically three properties for steel, because if we draw a stress strain diagram, we know that steel generally has a linear elastic portion, which gives you E. It hits a yield point and then does strain hardening and ruptures. So here would be better arrow. Here, at that point, we call that Fy. And at the end, here, we have Fu. If we look at a composite material that I'm tested, like I've tested, we only have Tu, which is the ultimate tensile stress, and E. This means that composites behave in a fundamentally different behavior in that a composite material is only linear elastic until it fails. Now, civil engineers are generally very, very conservative. So generally in our designs, we'll use up to Fy and use all of this strain. And you'll notice that if this is a stress-strain diagram, that the linear elastic strain is much less than the plastic strain. And we usually use all this plastic behavior to make our designs safer and more conservative. We'll get more into those details when we start looking at reinforced concrete design of beams and steel design of beams. But composites being new, they only have a linear elastic behavior, and then they fail. So that can make them be a little trickier when you're doing a design. Now, we've talked about a bunch of different material properties, and in this class, we're going to look at how we determine all of these properties and where they come from. Now, we're going to start with what might be my favorite material, which is concrete. I like concrete because it's cheap, and I like concrete because I've worked with it a long time. I think I was probably like 10 or 11 when my grandfather had me make concrete for the very first time. Now, there are two types of concrete. There's Portland cement concrete, which is generally a more structural material, and there's asphalt concrete, which is still a structural material but doesn't really fall under the purview of structural engineers much. We use asphaltic concrete to make roads. We use Portland cement concrete to make roads, but also buildings and all kinds of other stuff. Now, Portland cement concrete has only 3 ingredients. It has aggregate, both coarse and fine, or stone and sand, Portland cement, and water. Asphaltic concrete has 2 ingredients. It has the aggregates, just like Portland cement concrete, and to bind it together, we use asphalt. Now, Portland cement concrete. There are 3 factors that you need to look at when you're designing Portland cement concrete. They're workability, strength, and durability. In terms of workability, if you have less water in your mix, you have a stiff mix, which makes it very hard to place. If you add more water, you have a loose mix, which makes it very easy to place. In terms of strength, the lower the ratio of water to cement, the stronger your concrete is. And in terms of durability, the lower the ratio of water cement, the higher the durability. So in the 3 things we have in concrete, we have the aggregate, we have the cement, and we have the water. The water-cement ratio is just the ratio of the water over the cement. Now, if we look at our 3 design parameters, workability, strength, and durability, we say that generally when we have more water, it is easier to place, and we have less water, it is hard to place. In terms of our strength, the more water we have, if we keep the amount of cement constant, the weaker our mix is going to be, and the more water we have, the less durable our mix is going to be. So generally, this defines the great divide in concrete. Because if you're an engineer, you generally want something that's strong and durable. But if you're a contractor, you're going to want something that is easier to place. So here begins the eternal struggle in concrete. The contractor would like a more workable mix that's easier for him to place. An engineer would like something with high strength and high durability. This basically puts the whole construction world and engineering world at odds and leads to a bunch of tests and things we do to ensure the quality of our concrete mixes. But the key to all concrete, or all Portland cement concrete, is the water-cement ratio, or the ratio of water to cement. Now, in terms of the components in concrete, Portland cement by far is the most expensive. Coarse aggregate and fine aggregate are about equal. These are kind of regional. So in New Jersey, fine aggregate is generally a little bit cheaper than coarse aggregate because New Jersey has a bunch of sand. And New Jersey gets most of its stone from Pennsylvania. New Jersey does have quarries. That's not saying there's no stone, but Pennsylvania generally has more stone as a resource. New Jersey has more sand as a resource. If you go into Pennsylvania, sand costs more than stone. But these are very regional, sand and stone. Portland cement, not so regional. It gets shipped around. But one interesting thing about concrete is it's a regional material. So the concrete you have in the Northeast is different than the concrete you have in the Southwest because you're not shipping aggregate and sand across the country. The cheapest thing in concrete is water, by far. Now, we're going to go into very complex concrete design, but just so you can always have a concrete design in your mind, and contractors won't make fun of you on the site when they're like, well, we need to make some concrete, and you're like, well, let me go do this advanced complex calculation. Before we had ACI mix design, we had very simple volumetric mixes that you could buy books that had all kinds of different volumetric mixes in them. The most simplest of these is the old school 1, 2, 3 mix, where you add by volume 1 increment of cement to 2 increments of sand to 3 increments of stone, and then you add water until it is workable. Now, adding water until it's workable is a trick. I don't know if I've ever gotten it right. It really depends on who's in charge of you when you're making this mix. They're the task holders of what is workable and what's not workable. So if you were sitting down with me making this mix, generally you do 1, 2, 3, you'd add water, you make a nice mix, and I'd come over and say, there's too much water. And then you'd be like, and then maybe you make another mix and you'd make it with less water, and then I'd come over and I'd say, well, there's not enough water. I think only one time ever have I made a concrete mix correctly in the eyes of a superior. But one thing you can always remember, if you need to make a concrete mix, and this mix will be anywhere between like 3,500 to 4,500 psi, if you have 1 volumetric increment of cement to 2 volumetric increments of sand to 3 volumetric increments of stone, you will have a viable concrete mix. And this volumetric mix could be it could be buckets, it could be shovelfuls. This will generally turn you out with a nice concrete mix. So now you'll have enough concrete knowledge to walk out onto a job site and not be made fun of by a contractor.